Alright, welcome to the third installment of unit number 5, which only has 4 parts, so we're over halfway there, where we're going to talk about the impulse momentum theorem. So let's just take a recall of some equations that we've seen so far. So we've seen that momentum is m times velocity. We've seen that impulse is the F net times the time. And we've also seen a slightly different version of Newton's second law with change in momentum over time. Now, something that we've used to solve a couple of problems already, but we're going to give it a formal name and we're going to make the connection where we have the impulse momentum theorem. And it isn't too hard to see that we can set J as impulse is equal to our change in momentum. Now, that's hopefully not something that seems shocking, where if we said J is F net times delta t, this would be equal to our change in momentum. So that's the impulse momentum theorem. It's just relating impulse and momentum through an equation. So what does this relationship mean? It means that a net force can cause a change in momentum. But that doesn't mean that they're the same thing. Impulse isn't momentum. We're just looking at a change in momentum. So it is not the same thing as momentum. To think about this, if you want to think about an analogy of if you get hit in the shoulder, it's going to hurt you. And then if you get hit harder, it hurts more. So there's a relationship between the strength of a hit and how much it hurts. But we can easily see that a hit is not the same thing as having a sore shoulder. So it's just something that causes it. So the impulse causes a change in momentum, but an impulse is not momentum. Momentum is separate and impulse is something else. So there are two different things, but they are related through this equation. So let's look at an example where we've got a 2,300 kilogram car slowing down from 15 meters per second west to 7 meters per second west. What is the car's change in momentum? So we're just looking at change in momentum, which is the change in mv. Now, this car is the same car, same mass, so we can just take the mass out of our delta because it's not going to change, which we can expand to be v minus v naught. And now we just need to plug in our numbers, 2,300 kilograms times 7.0 meters per second west minus 15.0 meters per second west. And after a little bit of math, that's going to give you negative 1.8 times 10 to the 4 kilogram meter per second west. Now you can also certainly write this as the change in momentum is 1.8 times 10 to the 4 kilogram meter per second east. So we figured out the change in momentum. So that's A. Now let's take a look at B. B asked us for if it takes 2 seconds to slow down, what is the net force? So now we got to use a little bit of our impulse momentum theorem. So we're looking for net force, and net force is hidden in impulse as J equals F net times time. So if we rearrange that, we've got F net is J over delta T. But we know from our equation up here that J is the same thing as delta P. So we can replace J with delta P over delta T, which we see there is that that's the same thing as Newton's second law in its different form. And now we can just plug in our numbers. We're 1.8 times 10 to the 4 kilogram meter per second east all over 2.0 seconds. And that's going to give us 9.0 times 10 to the 3 newtons. And if you are careful with your units, you should see that the newtons do come out of that kilogram meter per second squared, but there's our answer for the F net. So that's just how we use the impulse momentum theorem, as we've done already in a couple of examples. So in terms of this part of the notes, we're actually going to do this in class. So if you want to think ahead of time of choose one of the two. So you're doing car or a baseball, and you're to think of two situations that have the same change in momentum. So either two situations with a car or two situations with a baseball that have the same change in momentum, and you're gonna think about how the force and time are then different in those situations. But we'll go through that in class. So let's look at this example at the bottom. A 2,200 kilogram vehicle traveling at 94 kilometers an hour can be stopped in 21 seconds by gently applying the brakes. It can be stopped in 3.8 seconds by slamming on the brakes, or 0.22 seconds if it hits a concrete wall. I don't recommend the concrete wall option, might hurt. But let's take a look at finding the net force for each of these situations. So one thing we have to notice though, if we notice in all the situations, the change in momentum is equal because we're just going from the same starting velocity to the same ending one. So our equation for F net is going to be delta P over delta T. So if we figure out delta P, that makes our calculations very easy for F net. We don't have to redo a lot of calculations. So we're going to actually figure out delta P first. So we have delta mv, which we know is going to be mass times v minus v naught, which is going to be 2,200 kilograms, and 0 minus, we have to convert the 94 kilometers an hour to meters per second, and you're going to get a number for this of 57,444.44 kilogram meter per second. So that's our change in momentum for both cases. Now that you have that, you can do F net of 1 is going to be change in P over time 1. F net 2 will be change in P over T2, and F net 3 will be change in P over T3. Now, if you calculate this out, you would get F net 1 should be negative 2.7 times 10 to the 3 newtons. F net of 2 will be negative 1.5 times 10 to the 4 newtons, and F net 3 is negative 2.6 times 10 to the 5 newtons. Now our change of momentum is negative because we went from a positive velocity to 0, so our force applied has to be in that negative direction because we're going positive and our force is stopping us. So it does have to be negative, so that answer makes sense. The force increases at the shorter time, which also makes sense. So our answers make sense, and it's always good to think about making sure your answers make sense by the time you're done, because sometimes you make a small mistake, either converting 94 kilometers an hour wrong, and it totally throws your answers off. So we'll go over the other parts of the notes in class, and as always, physics is awesome.